Hello and welcome to our YouTube channel, Nanomagnetism and Magnonics. We are a research group from the University of Vienna, Austria, and we are specialized, as you may have guessed, in magnetism. Also, scope of our interest includes spintronics, superconductivity, and many more. So if you're interested, if you would like to know more, to learn more, don't hesitate to subscribe and follow us in order not to miss any new videos. As for now, I would like to introduce you and perhaps interest you in the field of semiconductor spintronics. And to be precise, in ternary and quaternary compounds, gallium manganese arsenide and gallium manganese bismuth arsenide. How magnetization manipulation in the thin layers could be a background for the concepts of magnetic memory. And let us start. And before, of course, proceeding further, I would like to acknowledge all people without whom this work just simply could not be done. Most of it was the part of my PhD work, which was performed in Institute of Physics, Polish Academy of Sciences, Warsaw, Poland. And I would like to give a special shout out to my supervisor, Professor Tadeusz Wyszyński, Dr. Tomasz Kandrarczyk, and Professor Tadeusz Wykielski. Also, special thanks to outstanding scientists and colleagues that helped to perform the structural analysis, magnetic analysis, that grew our samples, and help in general to make this thing work. I would like to start slow and steady to give you a small introduction. Why spintronics? Why these materials? So this will be covered in these first two sections. Further, when we will establish why it is important and what are we working with, I would like to introduce the actual results of the samples in the section structural analysis and magnetic analysis, and in the end, some Magneto-transport properties. The last three sections altogether combined will give us insight of how this would work as a magnetic memory concept. Let us begin. It was in 1946 when the grandfather or father of modern computers was born. It was built by John Mauchly and John Eckert and was called ENIAC-1, or the Electrical Numerical Integrator and Calculator. This was sponsored by the American military because they needed a true high-tech computer for calculating artillery firing tables. In just 1 second, this beast was able to perform 5,000 of simple addition operations. You see, what was impressive in 1946, the standards changed. And now the high-end desktop market models of the processors are able to perform about millions of MIPS, or millions of instructions per second. The same evolution happened with the magnetic memory. You know that traditional spinning hard drive is a basic storage in your computer. The phenomena behind it is GMR, giant magnetoresistance. It was acknowledged by a Nobel Prize as recently as 2007. Albert Ferd and Peter Greenberg got the Nobel Prize, by the way. And a hard drive is essentially a metal platter with a magnetic coating that stores your data. And read-write head on the arm accesses the data while the platter is spinning. Moreover, we also have now the SSD, which performs the same basic function as a hard drive, but data is instead stored on the interconnected flash memory chips that retain the data even when there is no power flowing through them. So, how do we retain this pace of evolution? How do we make sure that we will get better and better technology and not stop and stuck at some point? Well, could be the spintronics the answer to this question. Let us see. In modern information system, logic and memory device based on semiconductors are playing essential roles. They're made of transistors and integrated circuits, in which the charge transport accumulation are used for information processing. And by making the transistors, as you know, on this slide, by making them smaller and smaller and smaller, yes, we were able to improve the speed, to the capacity, cost per bit, and this contribute to the advancement of computers and information system. which is basically so-called Moore's law. You get better generations of, for example, processes, but in comparison, you are paying even less. But already at these sizes, at the nanometers, tens of nanometers and below, we are getting to some basic issues, like energy dissipation is becoming more and more serious. Another one, that semiconductor devices, most of them are volatile, and power supplies or batteries are necessary to maintain the internal state of these devices. For example, if these semiconductors, the semiconductor material and devices, would have some of the properties from the magnetic devices, we will be able to create a new class of functional materials which have high-speed logic and non-volatile memory, electrical gating and spin transport, fast switching, and manipulation of the material properties by doping. So, in other words, if we combine the best of two worlds of semiconductivity and magnetism, would be able to have new leap in the technology. Furthermore, using magnetization directions of magnetic materials, paramagnetic materials, we will be able to create not only non-volatile memory logic devices, but also be able to reprogram or reconfigure these logic devices. And this new spintronic approach based on the semiconductors that could be suitable and useful for the future information technologies, such as neuromorphic computing and artificial intelligence that for now are not accessible with the current state of technology. So this is actually the scope of spintronics. What is spintronics? Spintronics or spin electronics allows to use spin properties instead of or in addition to charge degrees of freedom. And current efforts in designing and manufacturing spintronic devices involve two approaches. The first is already mentioned, perfection of existing GMR-based technology by either developing new materials with something just called large spin polarization of electrons, or making improvements of variations in the existing devices that allows for better spin filtering. The second effort, which is more radical, focuses on finding novel ways of generation and utilization of spin polarized currents, investigation of spin transport in all semiconductor device geometries. And here we have a new class of materials which comes into play, dilute magnetic semiconductors, that will allow to store, process, and transfer the information. So what are dilute magnetic semiconductors? What makes them so attractive? Perhaps even more importantly, it would be much easier for the novel devices that are built upon the material, which includes semiconductors, to be integrated with traditional semiconductor technology, because it won't require re-establishing or reimagining of already existing technology base, but just improving it. And such new devices would be compatible or partially compatible with existing base. So a few words about semiconductor. It's a material which has conductivity or resistance falling between that of a conductor, such as copper or iron, and insulator, such as plastic or rubber. Its resistance falls as the temperature rises, and metals are, as you know, the opposite. The possibility to change the physical properties with an applied electrical field is one of the key features of the semiconducting materials. One of the most well-known semiconductor is, of course, silicon, and we find it in electronics, in solar cells, photonics, and so on. Silicon and germanium are well-known semiconductors with properties close to insulator in their intrinsic or undoped state. Another key feature of semiconductors, if you add a small amount of dopant, that would cause the electrical resistance to drop greatly, turning them into N-type or P-type semiconductor. And the conductivity of this deliberately contaminated, for example, silicon crystal, can be increased by a factor of the 10 to the power of 6. Semiconductor made of several elements are called compound semiconductors, in contrast to the single one. A compound is a substance formed when two or more chemical elements are chemically bonded together. In mixtures, the substances present are not chemically bounded. The type of bonds that are usually holding elements together, most common at least, are covalent and ionic bonds. So when you see, for example, gallium arsenide in group 3,5, it means that we have one element from the group 3 of the periodic table, gallium, and we made a compound with the element from the group 5 from the periodic table, arsenic. This new material is chemically bonded, so acting like a new one, like a Lego brick. Let us look at the doping again on the example of silicon. As a silicon, it's a material with 14 electrons, 4 valent electrons on the outer shell, 2 on the 3s and 2 on the 3p subshell. In the case of n-type doping, so here is our silicon group 4, we add for the n-type doping material from the group 5, phosphorus or arsenic. Group 5 just tells us that it has 5 electrons on their outer orbital, on their p orbital. And since the 5th electron from arsenic or phosphorus has nothing to bond to, it is free to move around, allowing the electric current to flow through the silicon. In the case of p-type doping, we're adding, for example, boron, and we are creating the same situation, but here the charge carriers are not electrons, but holes. So here I would like to underline gallium arsenide, which was deliberately left out of the equation for some time. Gallium arsenide has some electronic properties which are superior to those of silicon. It has a higher saturated electron velocity and higher electron mobility. That is, you can shoot electrons across a transistor faster, get higher gain, higher bandwidth out of transistors, and get better conduction with lower doping levels. Also, the thermal conductivity is lower, as you may see. As a rule of thumb, lower is better because then material conducts less heat energy. Unlike silicon cells, gallium arsenide cells are relatively insensitive to heat. Gallium arsenide devices, say, generate less noise at higher frequencies. Usually, you will find gallium arsenide transistors in Wi-Fi receiver and transmitter, not silicon one. You almost certainly will see gallium arsenide in the heart of your cell phone's receiver and transmitter. Another advantage is that they can operate at higher power levels and have a higher breakdown voltage. These properties recommend gallium arsenide in mobile phones, satellite communications, microwave, P2P, point-to-point links, radar system, and so on. And direct band gap, which is also a big advantage because it means that it can be used to emit light efficiently. Let us look at the hole mobility. For now, gallium arsenide has a poor hole mobility. The key technology in the computer chip now is a CMOS, where you have the N-type and P-type transistor together to force some logic gates. And the currents through the N-type and P-type devices have to be balanced in order to have a well-functioning device. Otherwise, you get some difficult timing issues and other. And in order to balance the current, you need to somewhat a balance of electron and hole mobilities because you'll need to use the same properties on gate weights in order to balance the current. Let's look at the silicon. So electron and hole mobility. The ratio is, let us say, 3:1. That is, the P device have to be 3 times as wide as the N device. That is doable. But if we look at the gallium arsenide, that's becoming quite a challenge because of the ratio between electron and hole mobility. Second disadvantage of gallium arsenide is no oxide. So you have to perform a chemical vapor deposition to get an oxide or some nitride insulating layer on it. And even then it would be having worse quality, won't stick nearly as well as the natural oxide of silicon. CO2 is one of the best known insulators. So in other words, gallium arsenide makes very bad MOSFET transistors. Despite the disadvantages, as you may see, the market for the gallium arsenide is growing and is predicted to continue to grow, especially in the fields where it shines the best, such as satellite communication, high-frequency systems, and photovoltaic solar cells. But is there something that we can do to tune the parameters and be able to use this truly amazing material already in a wider range of applications? And the answer is yes. So we can add to already well-discussed gallium arsenide some transition metal, and we will arrive to something which is called dilute magnetic semiconductor, new class of materials. And among many semiconductor spintronics materials, generally for magnetic semiconductors already attracted much attention and had been studied worldwide. Why? Because the ternary, which means that this compound consists of 3 elements, though this gives the possibility to tune or change the lattice constant band parameters by changing the composition of material. And the random distribution of magnetic ions over the cation sublattice leads to important magnetic effects. The most characteristic feature of the DMS is a giant spin splitting, which increases the spin polarization of carriers and increasing the carrier concentration. Increasing usually the concentration of the transition metal ions may lead, at least in case of gallium manganese arsenide, lead to the appearance of ferromagnetic phase. How do you make a typical DMS? So take non-magnetic semiconductor, you take our nice gallium arsenide, and we substitute a part of the diamagnetic atoms with the atoms of transition metal, with manganese. And you will arrive to a highly diluted material. This is why we call it dilute magnetic semiconductor. This material is paramagnetic. DMS acts in the absence of external field like a semiconductor, but everything changes when the external field is applied, and it results in the strong spin splitting of the conduction band and the valence band. The origin of the spin splitting is the exchange coupling, SPD, between the delocalized carriers and the core spins. From now on, I'll be concentrating on the gallium manganese arsenide, but obviously in this class there are other subclasses like materials 2,6 and 4,6, just meaning that we have different combinations of materials from group 2 and 6 of periodic table or 4 and 6 of periodic table. But gallium manganese arsenide is the most promising one. Not because it is based on the gallium arsenide, but also, as it will be shown later, it exhibits really cool and interesting properties. So let us look what are the changes in the crystal potential of gallium arsenide, which is a host, when we add one single manganese impurity. But before proceeding, if you generally see this notation, so 2 elements separated by combined brackets for the compounds, it means that we are substituting the former gallium with the latter manganese. So the perturbation consists of 3 components. First being long-range Coulomb contribution. It's a long-range hydrogenic-like potential of a single acceptor in gallium arsenide, which produces a bound state around 30 milli-electron volts above the valence band. So a second contribution comes from the short-range central cell. It is specific to a given impurity, and it reflects the difference in the electronegativity between the impurity and the host atom. Let us take zinc, for example. It's a non-magnetic acceptor and the first nearest neighbor of gallium in the periodic table. When we add it to our gallium arsenide, for example, it would increase the binding energy by 5 milli-electron volts by substituting gallium. For manganese, which is the 6th nearest neighbors of gallium, the central cell contribution is again 30 milli-electron volts. The origins of this is in the p-level shift. And the last one, remaining part of the manganese binding energy is due to the spin-dependent hybridization of the manganese D state with neighboring arsenide P states. And when we combine all 3 of them, we will arrive to the experimental binding energy of around 0.1 electron volts. Again, binding energy is just the amount of energy required to separate a particle from a system. So this was with 1 manganese ion introduced into gallium arsenide. What will happen if we will start increasing the concentration? When we are still at the low concentration of manganese, around 0.5%, the distance between the holes bound to the manganese ions is much larger than the size of the bound hole, which leads to insulating phase. With a medium concentration between 0.5 and 1, we already see the overlapping to form impurity band and insulated metal phase. With a high concentration, it's 1 and more, we see the ferromagnetism at low temperatures. Because the impurities are closer and long-range Coulomb potentials are screened, leading to imperfect metal with disorder broadened and shifted bands. Impurity and host band are merged into one inseparable band, which tail may contain localized states depending on the concentration and disorder. So just like in other doped semiconductors, if the Mott criterion is fulfilled, the Mott criterion, it's if an average distance between holes becomes smaller than 2.5 acceptable radius, the Anderson-Mott insulated to metal transition occurs. The fact that the hole ceased to be bound to the manganese ions is seen in charge transport, in magnetic circular dichroism, and electron paramagnetic resonance. With a concentration of manganese above 1%, we arrive to a gallium manganese arsenide as we know it, one of the best studied semiconductor spintronics material. Again, it is DMS, dilute magnetic semiconductor, which consists of non-magnetic base, well-known, well-established, and well-compatible with existing technology, doped with some transition metal ions, usually manganese, that has a spin moment of 5 seconds. It's a ferromagnet, where the magnetism is governed by the exchange interaction between manganese's 3D moments and delocalized charge carriers. So it means that it's magnetic below some critical temperature, which is called critical temperature, and paramagnetic above it. Especially important are the growth parameters, the concentration of dopants, the choice of the buffer and substrates, and so on. They influences the outcome results and parameters of our material. And despite already having a well-established base of a concept devices for the gallium manganese arsenide, as you may see here, we decided in our research to go even further, to add one more element, bismuth, which is one of the heaviest stable element of the fifth group. It has high electrical resistance, it's a naturally diamagnetic element, and when incorporated into gallium arsenide, for example, it decreases band gap and increases spin-orbit coupling, the latter being especially important, as you may see. From now on, I'll be giving you results of the actual measurements performed on the gallium manganese arsenide and gallium manganese bismuth arsenides in films. And by thin, I really mean thin, with a thickness varying from 10 to 100 nanometers, a concentration of manganesum from 4 to 6, and bismuth, if present, from 0.3 to 1. Also, we have a different scheme of our sample growth. Typical method of growth is molecular beam epitaxy, or low temperature molecular beam epitaxy. For this, you need to have a substrate on which you grow ternary compound. And if you grow gallium manganese arsenide on top of gallium arsenide, you are introducing compressive biaxial strain to it, because lattice parameters of the gallium manganese arsenide are larger than of layer below. So we are trying to compress and to squeeze the top layer to fit the bottom one. In a case, if there is a buffer layer, indium gallium arsenide, we are introducing tensile strain. So we are stretching the top layer to fit the lattice perimeter of the layer below. Why it is important? Because it strongly influences the crystalline anisotropy, as will be seen further. And we'll be having completely different magnetizations, just depending on the growth parameters. Also, just quick note, if not mentioned otherwise, the results are given for the annealed samples. Usually after the low temperature molecular beam epitaxy growth, there is some concentration of native defects, manganese interstitials. They are not built in the lattice, but they are sitting in the interlattice position. And in order to get rid of them, you usually heat the material. In this case, it was annealed in air for some prolonged period of time. And this is proved, this is well known and established to improve the structural characteristics and enhance the carrier concentration. And this is a life of the dilute magnetic semiconductor sample. We start with a growing procedure, being again low temperature molecular beam epitaxy. Then after obtaining samples and going with some post-growth treatment, being annealing, we proceed to analyzing whether we have good samples. So structural analyses are important at this stage. The best samples are then chosen, and on them we perform some lithography patterning if we want to do one. After that, we bond the contacts on top using some indium and golden wires and perform the Magneto-transport measurements, usually in a helium temperature, 4.2 kelvins. This last stage wasn't still achieved, spoiler alert. Still, I hope one day we will get to it. For now, I would like to go through all of them in our presentation. And with this, we arrive to the structural analysis. So let us start the structural analysis with a transmission electron microscopy, which was performed on the 50 nanometer thick ternary and quaternary compounds grown on the gallium arsenide buffer, as you may see on this scheme. So the sample are under compressive biaxial strain. Again, thickness is 50 nanometer, concentration of manganese is 6%, concentration of bismuth if present is 1%. The heavier atoms are observed, the lighter is the contrast in the area, as expected from the secondary electron microscopy signal. Also, a guide for the eye are crystallographic directions that are corresponding to the lattice layer orientation. They are mapped on the image, as you may see. The only thing under question is this cloudy contrast here on the right-hand side, and it originates from uneven thickness of the tinfoil, as no defects like mosaicity or dislocations are visible in the vicinity. Just looking at the 10 nanometer scale, we may see that both ternary and quaternary compounds of two distinct color hues show perfect zinc-blank structure with absence of defects. But images taken at various sample spots and in various scales in general show high-quality structures with minor defects. High quality of the films was also confirmed by other techniques, namely high-resolution X-ray diffractometry and secondary mass spectroscopy. So let us start with the first one. High-resolution X-ray diffractometry is an important technique for characterizing quality of the crystalline structure of the measured material. We are studying the individual Bragg peaks of the single crystals and thin films, and further analyzing sample scattering intensity as a function of outgoing direction. Why it's good? It's quick, it's non-destructive, it's high sensitivity with respect to small changes of the lattice perimeters, and allows to study epitaxial layers of few nanometers thick. So one would expect a cubic crystal structure for the gallium manganese arsenide because gallium arsenide exhibits it. A cubic crystal structure, just to remind, has the highest symmetry. But due to the epitaxial growth of the bigger lattice unit system of gallium manganese arsenide upon the smaller one, gallium arsenide, the layer symmetry lowers. So that is why I'm telling that we are compressing the top layer to the bottom one. And this, in fact, it results in tetragonal deformation of the lattice unit. On the images that are seen here on the left down corner are the results of the reciprocal lattice maps measured along -2, -2, 4 crystallographic directions. The measurements were performed on the same set of samples, perhaps even same samples, as in the previous transmission electron microscopy measurements. All the reciprocal maps shows Bragg reflection peaks from the corresponding layers. They are all visible. The sharpest one, the most distinct one, obviously belonging to the substrate. It's colored in red. And the broader one originates from the either ternary or quaternary compound. Also, they lie on the same cytomorphic line, meaning that lattice in plane perimeters fitting of the upper film respect to the one below is quite good. Peaks, as you may see, are well separated and they're distinguishable from each other. This is a signal of a good crystalline quality. The same result could be said for the secondary mass spectroscopy, but let us look at this more details. So SIMS, it's one of the most sensitive surface and thin films analytical techniques for detection of the composition. It uses internally generated beams of ions, which is focused on sample to generate gas phase ions by electron ionization that are further transferred to the mass spectrometer and separated according to a specific mass to charge ratio. And they are called secondary ions. Those are secondary ions mass spectroscopy name, SIMS. Analysis consumes very little of the sample and making it essentially, again, a non-destructive one. And also it is very quick, detrimental for checking the homogeneity of the layers. On the images you may see on the right top corner, on the left-hand side on the axis is a manganese atom concentration per volume unit per centimeter cubic. And the right axis is a concentration of other components, while here is a penetration depth of the corresponding signal. So what does it mean? That we expect gallium, manganese, and arsenide in a case of ternary compound, and gallium, manganese, and bismuth arsenide in a case of quaternary compound. Below it is a buffer, again, gallium and arsenide only. So after 50 nanometers, we should see only signals from gallium and arsenide in both the cases. And it is the case in our samples. So you may see that manganese is present only for the first 50 nanometers. After that, the signal drops down. And for the quaternary compounds, the signal from bismuth also drops around 50 nanometers. Relatively low decline angle in the endomanganese dopant curve is connected with the interlayer out diffusion of atoms, mostly into a buffer underneath. It happened during the growth procedure. Another dropout in the signal visible per first few nanometers, let us say specifically for manganese, is understood as a result of the post-growth treatment, annealing treatment, which resulted in more active atom out diffusion to the surface in the shallow layers in comparison to those sitting deeper. Well, you see that SIMS technique identifies the signal from all atoms, both those that are built in the lattice and those that are in the interlattice positions. Again, those interstitial defects. And slightly lower, as you may see, signal from the gallium and arsenide in the beginning corresponds to the surface oxidation distortions. Otherwise, we may say that as proved by 3 techniques, we have a high quality samples with a good zinc blank lattice, low concentration of defects, homogeneous throughout whole layers. With that, we can proceed to the measurements, which are the magnetic analysis. We already established that growth conditions are crucial for the material's parameters. So let us look into the anisotropy. Depending on which buffer we choose, for example, the gallium arsenide with lower lattice parameters than the top layer, or indium gallium arsenide with high lattice parameters than of top layer, we may arrive to different set of easy magnetization axes. Here they are indicated by the deepest energy minima. Easy magnetization axes are formed to minimize a carrier's total energy needed to preserve the ferromagnetic state for a collective macroscopic magnetization of manganese moments. This is driven by the Fermi level position in the valence band or magnetization-dependent exchange splitting. Thus, it's dependent on the hole concentration and the temperature. In the case of gallium arsenide, we have a biaxial compressive strain, as it was mentioned earlier. It means, as it's brilliantly illustrated on these pictures, these magnetostatic free energy surfaces derived from the Magneto-transport measurements under different applied magnetic fields in low temperatures. So in the case here, we are having two easy directions. The first one is the original 100, which is a cubic anisotropy, and the second one being 110. Usually the situation for the compressively strained films is even a bit more complicated. So if layers have a high concentrations of valence band holes, then there is an inequality between -110 and 110. The former being more energetically preferable than the latter. In the case we have an indium gallium arsenide buffer, we are stretching again our top layer to fit to the buffer below, and this introduces only one crystallographic axis, easy magnetization axis, along 001. And this is confirmed by the superconducting quantum interference device measurements by the magnetization as a function of the applied magnetic field in low temperatures. So for the simplest growth on a gallium arsenide, the easiest magnetization direction will correspond to hysteresis with more square-like shape with a higher magnitude. And it is the case for 100 for both ternary and quaternary compound. Then there is again, as mentioned, -110, which is unequal to the 110, which is the hardest easy axis for our material. The addition of 1% of bismuth did not change the situation with anisotropy. Actually, these measurements were performed on the same set of samples that prove itself of high quality during the crystallographic structural check. And in the case of indium gallium arsenide buffer, we see that there is already some skew introduced into our hysteresis, which is less visible in the case of ternary, indicated by black, but is way more visible for the quaternary compound, which means that there is probably, in addition to this 1001, or perpendicular to the surface easy axis, some additional axis arises. If to look at the magnitude as function of the temperature, we may derive a whole graal of all the magnetic measurements, which is Curie temperature. Curie temperature is when the curve is flattened. The measurements were conducted along the three easy directions, and they all come to one line in the end. For ternary compounds, the Curie temperature is around 110 kelvins, while for quaternary compounds, it's more like between 90 and 100 kelvins. The temperature was enhanced for the samples grown on indium gallium arsenide, though, with 140 for ternary and 100 kelvins for quaternary compounds. And this is only the original crystalline anisotropy, which we can manipulate by introducing different buffers, also different dopants, like, for example, bismuth. We also can play and introduce artificial shape-dependent anisotropy by patterning our layer in such a way that top layer is such thin that the strain-induced relaxation processes are forcing our layer to be aligned for the spins of the magnetic ions in our top layer to be aligned along, for example, a very thin stripe patterned by the lithography. This we will see further. And here we see one of the key limitations for the gallium manganese arsenide, namely that its TC, the temperature, again, below which it's magnetic, paramagnetic, and above which paramagnetic, or almost non-magnetic. It's well below the room temperature, which is 300 kelvins. And here we have 140 at best. Actually, the best gallium manganese arsenide layers, they showed TC around 200 for the bulk materials and 210 for the 2D structures. Despite this, I would still call it a success because this material has a history of improvements of its TC. It already overcame once in its history the limitations by lowering the growth temperature. Perhaps in the future, new improvements will be introduced and we will have same high quality material, but with even higher TC. For now, I would like to say that we observe a relatively high TC for magnetic spin ordering, well below Curie temperature in all the investigated layers. And with this, we arrive to the final part of the presentations, the Magneto-transport properties. And here you may see one of my alma mater, Institute of Physics, Polish Academy of Sciences in Warsaw, Poland, where not only most of the results that I present today are collected, but also where I have spent a great 6 years doing PhD and further working. On the top photo, you may see the setup for low temperature, low fields transport measurements, on which most of the magnetotransport data that will be shown today were obtained. Not only it was work, but we had time for traveling, for visiting conferences, great thing to do when there is no coronavirus. And here is definitely a quality time that we had while discussing some physics topics. And coming back to the topic of our discussion, during our measurements, we were using a low frequency locking technique to analyze 2- and 4-point probe longitudinal magnetoresistance and Hall resistance as a function of the applied field. We were applying field both in plane and out of plane at low temperatures. All measurements were taken in helium, 4.2 kelvins. Measurement setup consisted of the current source, which is voltage controlled, 2 interconnected lock-in amplifiers that are further connected to the outputs on the sample low temperature insert through the voltage preamplifiers. On the low temperature itself, there is a sample mount table, which is not visible here, with a removable coil on top. Then there are 8 electrical wires hidden inside the stainless steel pipe, connecting the sample contacts on the mount table, which is a cold side, with externally hermetically sealed BNC connectors, hot side of the insert. And then we had a helium tank. We had different mount tables. So cables on the right were typically soldered with those on coil. Coil was able to produce a field as large as plus minus 950, 980 Oersted. Pins on the left were joined to the sample's handle respective pinholes that connects upper box contacts outputs and contacts on the sample through inner cables. Then a fully mounted holder is later slowly cooled while being inserted into the helium tank. After a quick check of the contact's resistance and low temperature, then we proceeded to connect cables here on top and do the measurements. So one of the key phenomena in most of the magnetotransport measurements is the Hall effect, because it gives us an insight into a lot of materials parameters. Let us repeat it in a few words. If we have a thin conductive plate like this, and we set current to flow through it, the charge carriers would flow just in a straight line from one side of plate to another. Everything will change if the magnetic field is applied normal to its surface. If it brings it to the plate, we disturb the straight flow of the charge carriers due to the force called a Lorentz force, expressed by this equation, where E is the charge of electron that is moving with a velocity v. In such a case, the electrons would be deflected to one side of the plate, while holes would be deflected to another side of the plate. This means that we put a meter now between the sides of the plate, we will be able to measure the Hall voltage. The Lorentz force causes accumulation of charge depending on the polarity, and as a result, there is an electrical field generated in a direction perpendicular to both the current flow and the magnetic field. And the accumulation will continue until the field generated is sufficient to stop any further flow of charges. The general expression of the Lorentz force is given in the top equation here. So after performing Hall measurements, we will obtain a set of parameters, among which is a Hall coefficient, Hall resistivity, which are connected via this formula in the case of the 2-dimensional or thin films. From that, we can determine the type of the prevailing charge carriers, holes or electrons, and their concentration. Usually, the Hall resistivity increases linearly with applied field, but it's not the case for the ferromagnets. You see, when the magnetic field is still weak, the resistivity will increase sharply until it will reach some saturation point. The magnetic field is strong enough, and then there will be plateau. So this equation describes the case for ferromagnet. And the first term in it is a classical Hall effect. It's linear in field, and it is a term that determines type and concentration of free carriers. For gallium manganese arsenide, it dominates in magnetic fields larger than 1 Tesla. The second term, though, it's proportional, as you see, to the magnetization and dominates in lower fields, and is called the anomalous Hall effect, where Ra is anomalous Hall coefficient. Ra depends on the material's parameters and, in particular, on the longitudinal resistivity. There are two origins of this magnetization-dependent term, and both are related to coupling between spin and orbital angular momentum. Extrinsic, disorder-related due to spin-dependent scattering on impurities, and intrinsic. And in such an experiment, charge carriers acquire an additional contribution to their group velocity perpendicular to the electric field and hence contributes to Hall effects. We will see it further on the example of gallium manganese arsenide. For gallium manganese arsenide, actually, there are more than one interesting transport phenomena in play. In addition to anomalous Hall effect, there is also a planar Hall effect. So let us say just a few words about each of them. Anomalous Hall effect, again, like we established, is similar to the classical Hall effect, though the charge carrier experiences a transfer force while moving in electric field. But this force is proportionate to the spin current, not to the charge current, like in Lorentz force. And in the end, we have separation of the charge carriers based on their spin direction, spin down or spin up. Like on this image, you may see that the electric field, the spin flow, and the spin direction are all mutually orthogonal. But in the case of the planar Hall effect, magnetization is tilted away from the electric field, but still not perpendicular to it. A charge current forms that flows along the magnetization direction. Since the charge current is spin polarized, the planar Hall effect also gives rise to a spin current. In other words, planar Hall effect is developed when the spontaneous transfer voltage is created due to the spin-orbit interaction in response to longitudinal current flow under in-plane magnetic field, or sometimes even in the absence of the magnetic field. Planar Hall effect is a transfer component of the anisotropic magnetoresistance, a larger phenomenon. So AMR usually occurs in ferromagnets and is a magnetic field-dependent response of the carriers, resulting in a change of electrical resistance. Here you may see two equations that are usually used to describe a single domain model, the longitudinal component and the transfer component. And both of them depend on angle theta between the direction of the magnetization and the current. In the equations, R parallel and R perpendicular are corresponding to the resistances when the current is either parallel to the magnetization or perpendicular to the magnetization. There are two main reasons for this effect. It is a spin-orbit coupling and magnetization. So let us see how this phenomena look during the measurement. For this, we have chosen ternary and quaternary compounds from the 10 nanometer 6 series of samples with 6% of manganese and 1% of bismuth. They are all grown on the gallium arsenide. As you remember, only with such a buffer, we have the biaxial crystalline strain with in-plane a set of easy magnetization direction along cubic 100 and uniaxial -110 and 110. In the case of the indium gallium arsenide, we simply have tensile strain, which leads to out-of-plane magnetization along just 1001 crystallographic axis. So this is a sample. The contacts in this case were done manually. Those higher than expected Hall resistance values may be observed due to the non-ideal contact placements with respect to each other. This is the indium on the top of the sample, as well as the indium is melted in the sample base. Both the contacts on top of the sample and base are connected via the golden wire. The base is then mounted in the sample holder. The coil is put on top. The wires are soldered, and the cold end of the sample holder with the sample inside is put into helium. And that's how we proceed with measurements. Beforehand, samples are pre-magnetized to negative values, to -1 kilo-Erstat. And then we proceed to measure with the magnetic field being swept from plus to minus value, from plus 950 to minus 950 Erstat. The direction of sweep is shown by the arrows. So we start here from the 0, go to the plus side of the field, come to some point, recurrence point, where the negative slope is observed, and then coming back, coming to the same starting point in the 0 field, and symmetric hysteresis on the other side of the field. So what do we see? That after high enough field is applied, magnetization vector in the layer is forced to be directed along the external magnetic field. And it's typically is shown with a negative slope curve in this, for example, magnetoresistance. So the full ferromagnetic order of the gallium manganese arsenide and gallium manganese bismuth arsenide spins in low temperatures about some critical point, which is a recurrence point, is characterized by the negative magnetoresistance due to the suppressed quantum interference contribution to the resistivity, for example, which is caused by effect of weak localization. The difference in here, for example, this is a longitudinal component, this is a transfer component. The difference in here being that the field and current are both applied along the -110 direction, while here the current is along -110 and field is along a harder magnetization axis, being 110. So let us see how the measurement is proceeding in more details, and especially in the area of our interest between the recurrence points, on the example of the planar hole effect. So in both longitudinal and planar hole effects measurements, the magnetic field sweep causes a rotation of the magnetization in the films by 360 degrees. The rotation, let me start the animation again. So the rotation is between a set of easy in-plane cubic directions. So this is a family of cubic planes, 1, 0, 0. We're starting with 0, -1, 0, and going a full circle. And this results in a 4 transition between low and high values. So these extremas, 1, 2, 3, and 4, corresponds to the angle theta equal to 45 and its cubic equivalents, 135, 225, and 315. Let's just come back for a second to underline a point which will be crucial in a few slides. So while we were comparing ternary and quaternary compounds earlier, from the structural point of view, we established that they both have good quality. From the magnetic point of view, they have the same crystalline anisotropy dependent on different buffers with the same set of the magnetization easy axis directions, though some of the perimeters, like Curie temperature, were lowered. For the transport, we see that as well, same phenomena are governing both ternary and quaternary compounds in low temperature and low fields. But comparing the two curves, we see the distinguishable increase of the magnitude, increase of the coercive field, and increase of the anisotropy field in the case of addition of bismuth. And this will be important for us in just a few seconds. So this all, frankly speaking, it was a preludium to be able to play further with these materials. Now we know that both ternary and quaternary compounds have good quality. We know what are the magnetization and transport phenomena governing its behavior. We can investigate, for example, magnetic domain walls in such nanostructures. And the ferromagnetic nanostructures in generally, you see, they open new possibilities for the magnetism-induced spintronic devices, such as magnetic logic gates and non-volatile memory cells. And here we are manipulating with a field, but not only with a field can we play. We can change the structure signal and manipulate it by a spin polarized current. So exert a torque on a localized magnetic moments by spin transfer. A threshold current for an activation of the domain wall motion in the gallium manganese arsenide is 2 orders of magnitude smaller than in classical metallic ferromagnets, shown earlier by many groups experimentally and theoretically, and is a big advantage for this class of materials. For now, let us concentrate at the materials at our hands. So we described the crystalline strain-induced magnetic anisotropy, that it leads to either in-play AMR or perpendicular magnetization. But also it is possible to introduce a pattern-induced anisotropy by smart lithography network. Smart nanostructurization of the layers that are grown under compressive strain will create an additional degree of freedom that can be used in device operation. So if a fabricates a ring segment, middle segment narrow enough, or for example, the cross stripe narrow enough, less than 100 nanometer, then this will tend to align the spin magnetic moments along the stripe or the ring segment. And this is caused by the misfit strain relaxation perpendicular to the stripe or the ring axis. So basically, we will have the spin alignment either in the configuration head to head or tail to tail. These are 2 domains in the case of nanoring and the domain wall separating them. We are manipulating the domain wall by applying sweeping magnetic field. So domain walls are the regions of inhomogeneous magnetizations, and they separate ferromagnetic domains of homogeneous magnetization. When obviously charge carriers are passing through domain walls in nanostructures, they exhibit spin-dependent scattering because there is reorientation from this direction to this direction. And this leads to additional contribution to the resistance, and that is seen on our measurements. Before going into details, it was shown that gallium manganese arsenide grown under compressive strain, the thin layers, they are simple single domain of the size of the hundreds of micrometers. This model where we assume that we have a single domain that could be separated by a domain wall by introducing slit here is applicable. So the contact pads, 4 contact pads, were all supplied with ohmic contacts, and the current was flowing throughout all the ring, while the resistance was measured through the middle segment. And we were able to observe the high and low states of the resistance. They were achieved through the additional contribution the charge carriers gain while passing through the domain wall area. This additional contribution manifested itself as a difference in resistance in 20-30 ohms for the gallium manganese arsenide. But as you may see, this was drastically enhanced in the structures with bismuth, at least by 2-3 times. And this is one of the reasons why we used bismuth in our structures. So we wanted to have a large difference in the cases of low and high resistance, because state of low resistance can be set as a 0, states of high resistance can be set as a 1. If we are having such a magnetic memory-like structure with such an encoding, obviously we want the difference between the 0 and 1 to be as large as possible. And that is why the increase of the magnitude and coercive fields that coming with addition of bismuth is such an important. What is even more interesting is the dependency of the cross-shaped nanostructures. Let us look at this. On the left-hand side, we see the AFM image of the nanocross. So there are 4 contact pads denoted with numbers, and there are the crystallographic axis along 0, 1, 0, and some angle alpha 8, which denotes along which direction was the magnetic field applied. So the general idea in this case was to create an imbalance between resistance responses along the two stripes. The current is flowing along them, and the resistance response is generated because of the different angles of the magnetocrystalline easy axis in the middle segment of the nano cross in comparison to the stripes. Let us interpret that. So again, like a nanoring, because we fabricate the stripe so narrow, we are forcing, because of the strain, spins of these segments to be aligned along them. So in the stripe 3, 4, for example, this, and 1, 2, example, this. But the middle segment, on the contrast to the previous design, it is unconstrained. There is nothing forcing the spins to be aligned along specific direction, and we see this nice 360 rotation depending on the application of the magnetic field. Which means if the current is flowing through the terminals 3, 4, the current should overcome only a 25 degrees difference between the spins in this segment and this segment. And here we basically have one domain, domain wall, another domain, domain wall, domain. In total, we have 5 domains and 4 domains walls. Contribution to the resistance from the scattering while passing these 2 domain walls will be lower in comparison when we measure the response from this stripe, because here it should overcome a 65 degrees difference. And it will result in a state of higher and lower resistance, which would be very stable in time and can be swapped with the opposite sign weak magnetic field or just a spin polarized current. So the principle of this functionality was checked by introducing different designs. A very important conclusion from this is that for the first time, nanostructures were fabricated from the gallium manganese bismuth arsenide layers. They show the non-monotonic magnetoresistive dependence on the in-plane magnetic field, similar to those of gallium manganese arsenide, but with an enhanced response that would be advantageous for the magnetic memory applications. And if you were wondering where the bismuth is actually changing any basic transport parameters like carrier concentration, then the answer is no. It decreases mobility, but on the tolerable level. All this was found out by performing a set of transport measurements, again, this time in higher fields. So remember, this was the anomalous Hall effect that we discussed earlier and that we were investigating in the previous slide. And this is the classical Hall effect from which the carrier type, p-type, holes, and carrier concentration was determined. The measurements were conducted in a set of 2 temperatures, 1.6 and 4.2. With this, we come to the conclusions. So the main conclusions are semiconductor-based magnetic materials like dilute magnetic semiconductor show great potential as a spintronic candidates due to the combination of well-established semiconductor base and advantageous magnetic properties like high speed and non-volatile memory. They are also compatible with the modern electronic space, and especially if we take gallium manganese arsenide, the model material for not only concept devices, but investigations of many interesting phenomena, whether it's anisotropy or it's a transport phenomena. Also, we were able to create nanostructures for the first time out of the quaternary compound gallium manganese bismuth arsenide. They showed enhanced spin-orbit coupling and improved features attractive for potential spintronic application. And with this, we have reached to the end. And I would like here to thank all of you who stayed with me till the very last slide. All of 2 of you. Thanks, Mom. Thanks, Dad. But in general, if you like the video, if you like the content, check out the videos on our YouTube channel. Click like, subscribe, and follow in order not to miss new information. For now, thank you for your patience and goodbye.